Hello, and welcome to the Introduction to Nuclear Chemistry and Balancing Nuclear Equations screencast. I'm Miss Willie, and today I'm going to teach you all about how your favorite superheroes got their radioactive superpowers. So let's get going. First, let's review what isotopic notation is. So in my diagram below, the element symbol is X. This is referring to the symbol from the periodic table. A is the mass number or nucleon number. If you remember, mass number was equal to the number of protons plus the number of neutrons. So, nucleon number, mass number equal, interchangeable vocabulary words. They mean the same thing. The atomic number is Z on my screen. This was equal to the number of protons inside of an atom. This also identifies the atom for which we are speaking about. So if the proton number changes, the atom changes. What is nuclear chemistry? Well, this is the study of the changes that happen inside the atom's nucleus. So we are very focused on the protons and the neutrons as nuclear chemists. A nuclide applies to a nucleus with a specified number of protons and neutrons. So if you remember, when we were first learning about isotopes, we would say the carbon-12 isotope because that is the mass number, that is the number of protons and neutrons inside the nucleus. Now, when as a nuclear chemist, they say the nuclide number. So they could say carbon-12, but that also is referring to the number of protons and neutrons inside the nucleus. Remember that total combined number of protons and neutrons is called the mass number or the nucleon number. There are two forces occurring inside the nucleus. The electrostatic force, which is that force that causes opposite electrical charges to attract to each other, or that Coulombic attraction. So inside the nucleus, all you have is protons and neutrons. Protons have that positive charge. So like charges repel. Neutrons allow for the strong force, which is the force between nucleons, to be stronger without increasing that electrostatic repulsion between the nucleons. So neutrons are very important to the nucleus of the atom. They are what holds it together. It helps that strong nuclear force, which is the glue or the cement. So without neutrons, those protons would just repel from each other and there would be no nucleus of an atom. A stable nucleus does not spontaneously emit any kind of radiation. An unstable nucleus has a tendency of emitting some kind of radiation, which makes it radioactive. Stable nuclei are characterized as having a ratio of neutrons to protons that is close to 1. So my example that I've given you is carbon-12. In carbon-12, I have 6 protons and 6 neutrons. So a 1-to-1 ratio. Whereas in the isotope carbon-14, I again have 6 protons because the identity of my atom did not change. Oops. 6 protons and 8 neutrons, which does not give me the 1-to-1 ratio. Carbon-12, stable, does not emit any radioactivity or radiation. Carbon-14, unstable, has to emit radiation in order to become stable. Not necessarily carbon-12. It could be a different product, and in fact, it is a different product. It is not carbon-12. So, the other thing I would like to discuss is the stability conditions. All atoms that are greater than number 83, so have greater than 83 protons, 84 and above, are unstable. They are radioactive. They are constantly trying to get to a stable state and are emitting radiation. Anything that is under 83 is unstable if there is the number of protons that are much greater than the number of neutrons, or if the number of protons is much fewer than the number of neutrons, they are unstable. If the protons are equal to the number of neutrons or is slightly smaller, then it is stable, which is in the case of carbon-13. So carbon-13 has 6 protons and 7 neutrons. This stable, very close to the 1-to-1 ratio. Carbon-12, stable, 1-to-1 ratio. Carbon-14, not stable, radioactive, not a 1-to-1 ratio. Next, nuclear chemists in general use the band of stability to help them determine whether or not an isotope is going to be stable or not. So they have graphed the number of protons on the x-axis of isotopes versus the number of neutrons of the isotopes on the y-axis. All of the isotopes found in the blue band are stable isotopes. As you can see, everything from about 1 to 20 has a stable isotope and is on that 1-to-1 ratio line. As you get above 20, it starts to deviate from that 1-to-1 ratio, and that's because as the number of protons increase, the ratio of neutrons to protons has to increase because there are more neutrons needed to compensate for that increasing proton to proton repulsion. So as I'm going above the 20, I need more neutrons, sometimes 2 and 3 neutrons, to compensate and help that strong nuclear force hold the nucleus together. Nuclei are radioactive or radionuclides, and the atoms containing these nuclei are radioisotopes. So when you use the term radioisotope, you're talking about the entire atom itself. When you're talking about a radionuclide, you would be just discussing what is inside that nucleus. So I'm only talking about protons and neutrons when I'm using the term radionuclide. When I'm using the term radioisotope, I'm talking about the entire atom itself. So what is radioactivity or radioactive decay? It's the process in which that unstable atomic nucleus loses energy by emitting radiation in the form of a particle or a wave to become stable. There are 3 main types of radioactive decay: alpha particles, beta particles, and gamma waves. So difference between a particle and a wave is that we know already that particles have mass, waves do not. Gamma radiation or gamma waves, if you remember from the electromagnetic spectrum, are very high energy, high frequency waves. When a radionuclide undergoes radioactive decay, nucleons are released or absorbed. The initial radionuclide is called the parent. As the parent undergoes spontaneous radioactive decay, the number of nuclear particles or nucleons changes. 2 major products are formed: a daughter isotope and either an alpha, a beta, or a gamma. What are the radioactive species? So a proton, P+, or a hydrogen isotope. Neutron, a neutron, just like what you see in the nucleus of the atom. An electron / a beta particle, a positron slash anti-beta, so this is the antimatter for the electron, an alpha particle, which is the same as the helium nucleus, and the gamma ray. Radioactive decay and penetrating power. So as a nuclear chemist, we are looking at the types of radiation. Remember, I'm an unstable nucleus and I'm trying to become stable. So I'm emitting radioactive particles and daughter isotopes that I am looking at how those penetrate or how those could potentially harm me. So an alpha particle and a beta particle, larger, have mass. Alpha particles are the largest, so they're stopped by paper or your clothing. They cannot get, or your skin, they cannot get into your body because they are so large. Beta particles are stopped by a piece of wood or aluminum, like aluminum foil, will stop a beta particle. Same as a gamma particle is a wave, so it is the most penetrating. It can go through paper, through wood or aluminum foil, and even through lead. You have to have at least a meter thick of lead bricks in order to stop in between you and that radiation source in order to stop and have it not penetrate into your body. Alpha decay and emission. So during alpha decay, an unstable large nucleus has too many protons. Remember that band of stability. So I'm high up on the number of protons and neutrons, so it will shed 2 protons and 2 neutrons in a packet called an alpha particle. Remember Rutherford? He is the one who coined the term alpha particle. An alpha particle is equivalent to a helium atom. Since an atom loses 2 protons during alpha decay, it changes from one element to another. This process is also called transmutation because the number of protons in the parent nuclide changes. So let's do an example problem. So write the balanced nuclear equation for the alpha decay of polonium-210. Down here at the bottom, so if it's alpha decay, the first thing that needs to pop into my mind is helium. So I'm going to know first and foremost, one of my products is an alpha particle, or I could write it as a helium. So the difference between nuclear equations and balancing these from chemical equations is that I'm concerned about the number of subatomic particles being balanced. This also follows that law of conservation. So the same number of subatomic particles that I began with on the reactant side has to be present on the product side. So right now, I have 4 nucleons on the product side and 2 protons, whereas I have 210 on the reactant side. So 210 minus 4 would give me 206. 84 minus 2 would give me 82. So now I can look at my periodic table to determine what the identity of that daughter isotope is. If I look at my periodic table, 82 should give me lead. So the daughter isotope of polonium-210 after alpha decay is lead 206 and an alpha particle. Beta decay or electron emission, so beta minus decay, is a neutron, which is a proton and an electron fused together. I know, crazy, mind blown. A proton, positive charge, and electron, negative charge, fuses together to have a neutral or no charge and create a neutron. in an unstable nucleus breaks down into a proton, which is kept in the nucleus, and an electron, which is emitted from the nucleus. So this electron comes from the breaking down of the neutron and is not from the electron cloud. This will drop the neutron count by 1 and increase the proton count by 1. Since an atom gains a proton, it changes from one element to another, a transmutation. Fun fact, krypton, which is our Earth version of kryptonite, is a beta electron emitter. So Superman will be affected by krypton or kryptonite's beta radiation. So let's do an example of beta minus decay electron emission. So write the balanced nuclear equation to the beta decay electron emission of potassium 42. So again, you have the beta. This time you know I have an electron that was emitted, so one of my products is going to be a beta particle, or I could write this as an electron because those are interchangeable. I have a -1 charge, so this is not a proton down here at the bottom. This is the charge of the beta particle. Then I have my daughter that I need to find. So if I look, what is Z plus 1? So what would be my protons plus 1? 19 plus 1 is 20. Then my A stays the same. So my mass number would stay the same. So calcium from the periodic table should be the next element one up that's gained a proton. And I know this is a little tricky. Students sometimes have a hard time wrapping their head around the 42, the mass number staying the same when I've had a change of neutrons and protons. So if I look at this, 42 minus 19 gives me 23. So that would be 23 neutrons in potassium 42. Whereas with calcium, 42 minus 20 would give me 22 neutrons inside of calcium 42. So the number of neutrons did change because it broke down to that proton and that electron. The next type of beta decay is beta plus decay. So now we're going to deal with that antimatter version of the electron, the positron. So a proton in the atom's nucleus breaks down into a neutron and a positron. This will increase the neutron count by 1 and drop the proton count by 1. Since an atom loses a proton during beta plus decay, it changes from one element to another, a transmutation. So let's do a practice problem. Write the balanced nuclear equation for the beta decay positron emission of copper 61. So first product I'm going to write is the positron, or the antimatter version of the electron. Either one of those is interchangeable. So then I'm going to write the daughter isotope that occurs when this releases or emits its radiation. So now I'm going to take one less proton. So instead of 29, I have 28 protons. My mass number stays the same. So I need to go to my periodic table and find 28, which is nickel. So the daughter isotope to the positron emission of copper 61 is nickel 61 and a beta, a positron. Next, we have electron capture. During electron capture, an electron in the atom's inner shell, so this electron comes from the electron cloud, not the nucleus, is drawn into the nucleus where it combines with a proton to form a neutron. This will increase the neutron number by 1 and drop the proton number by 1. Again, since an atom loses a proton during electron capture, it changes from one element to another, and I have a transmutation. So let's do an example. Write the balanced nuclear equation for the electron capture of 10(116). So this time, I'm absorbing an electron, so the electron will go on the reactant side of my nuclear equation, or this could be a beta. And then the resulting daughter isotope would be, so let's look, I'm losing a proton, so this becomes 49. My mass number stays the same because the number of neutrons and protons has to be equal on both sides of the equation. So now I just need to find out what 49 is on my periodic table. Which element is 49? 49 is indium. So the daughter isotope to 10(116) after electron capture is indium-116. Last but certainly not least is gamma decay or emission. During gamma decay, a nucleus changes from a higher energy state to a lower energy state through the emission of those electromagnetic gamma photons. The number of protons and neutrons in the nucleus does not change in this process, so the parent and the daughter atoms are the same chemical element. Can occur with other forms of decay simultaneously. Gamma emission was a lot of the type of radiation that changed your superheroes and giving them the superpowers that they want. The radioactive spider that bit Spider-Man went through gamma, a substance. The spider had walked through a liquid that was undergoing gamma radiation, and the Hulk had the same thing in his lab. He had gamma radiation that touched him and changed him into the Hulk. So let's do the example of gamma decay. Write the balanced nuclear equation for the gamma decay of beryllium. So remember, this is just a higher energy. So this is high energy. It relaxes. So the daughter is the same as the parent, and a gamma wave is emitted. So a summary of all of the different types of decay that we spoke about in the screencast: alpha decay, beta decay, positron emission, electron capture, and gamma emission, along with those generic equations, are on this slide. Let's compare nuclear versus chemical reactions. So in a chemical reaction, you involve loss, gain, and or sharing of electrons. The rates of the chemical reactions are affected by concentration, temperature, and pressure. Whereas nuclear reactions involve changes to the nucleus. Different isotopes of the same element may undergo different nuclear reactions, even though the element's isotope all share the same chemical characteristics. So lead, radioactive lead, is going to look just like stable lead. The rates of nuclear reactions are unaffected by concentration, temperature, and pressure, and nuclear reactions have larger energy transfer than chemical reactions. Thanks for listening, y'all.